you take out your highlighter, the first thing that we looked at was adding graphs. And in our other notes yesterday, all you do when you're adding graphs is just add the y values. Okay? But the things I want you to highlight here is some notation. Okay? If you're adding f of x plus g of x, this is the nice way to write it. F of x plus g of x. But there's also what I call the not nice way to write it. F plus g first in brackets and then x. So that yellow highlighted part and the green highlighted part mean the same thing. The yellow is easy to work with. The green can sometimes be confusing. And so as a result, I feel like the exam checks more often. Do you recognize the confusing notation? So at any time, because you'll get questions that say, hey, what is f plus g of 2? And it'll be written this way, and you'll be like, what? And you'll do some weird math, and it will be wrong. And it's not hard. All this means is f of 2 plus g of 2. And since f of 2 is the red one, that's equal to 2, right? Because f of 2 says when my x value is 2, what's my y value? 2. G of 2 says when my x value is 2, what's my y value? It's minus 1. And so 2 plus minus 1 is just 1. And sure enough, if we look at the graph, that green point shows up. Right? Because when you're adding graphs, you're just adding the y values together. Same thing happens with subtracting, multiplying, and dividing. The other thing that we notice is that if you're adding graphs, both graphs have to exist. So the domain of f of x is greater than minus 2. The domain of g of x is everything, but the green graph is only where both of them exist. So it's also greater than or equal to negative 2. So in all of these, we'll take out our highlighter again for subtracting. We'll do this rather quick. There's our subtracting functions. We have the not nice notation, and we have the nice notation. So my recommendation is whenever you have the not nice notation, like if you got f minus g of 2, write it as f of 2 minus g of 2. And again, the domain of subtracting fractions is where the two domains overlap. So they both have to exist to subtract. And multiplying. Now multiplying has a bunch of, here's the nice notation. It actually has a bunch of not nice notations. You could have f dot g, I guess, of 2. You could have f times g of 2 These are all examples of not nice notations. If you have any of these, change it to f of 2 times g of 2. And again, all we're doing is multiplying our y values. But with multiplying, there are some key points that you always want to look at. You want to look at and find for sure every place that the red graph and the blue graph are equal to 0. Because multiplying by 0 is super easy. Okay? I might also look at every place where the red graph or the blue graph is equal to 1. Because multiplying by 1 is easy. Okay? Why is multiplying by 0 easy? Well, 0 times anything is 0. So I'm going to put a green dot here and a green dot here before I reveal where the green graph is supposed to go. just to check if we're right. And if you multiply by 1, it's going to be exactly the same what the blue graph was. If the blue graph is 1 and you multiply the red graph, it's going to be exactly the same. So these are the points that I started with. Then if you have nice points, like for example, f of 2 and g of 2 is really nice. 2 times negative 1, that's going to be negative 2. That's another point. And I get the reveal. Does it go through all of those points that I drew? It does. The more points you multiply, the more accurate you're going to feel about your graph. But I did those 4 points, and my graph went through them perfectly. Also, again, notice the domain of f of x, g of x, p of x is where they overlap. Now we're going to turn to page 275. And right above here, they forgot to write it. So you can add dividing functions at the top there. So we can highlight that just like we highlighted on the other ones. And we can highlight the nice notation. Actually, the nice notation that I like, that's my nice notation. For dividing, I like to write it as a fraction. F of x divided by g of x. And our not nice notation, again, there is a couple of examples of not nice notation. So if you had this, or sometimes I've seen it like this, or sometimes I've seen it like this. Any of those notations like that, I would change it to equal f of 2 divided by g of 2. And you're just dividing the y values. Now, when dividing, it's important to recognize which function is in the numerator and which one is in the denominator. So I'm going to color code it based on my graph. The red one is in my numerator, the blue one is in my denominator. Because I have places on the graph where the red graph is 0, and I have places on the graph where the blue graph is 0, but they do different things now. In multiplying, they did the same thing. In dividing, if the red graph is 0, the green graph will be 0. If the blue graph is 0, I have a non-permissible value. Non-permissible values on graphs either show up as vertical asymptotes or as holes. In this unit, I'm going to say that 98% of the time, they show up as vertical asymptotes. The 2% of the time is when both of the graphs have crossed at the same place. That'll be a hole because you would have the same factor on the top and the same factor on the bottom, and that non-permissible value would cancel up. Okay? Other things that I would do, I would look for nice points. So obviously they have 2 divided by negative 1. That'll be negative 2. I would choose this point right here. This point 1 and this point is 2. If you did 1 divided by 2, you would get 1/2. I would look for the point where the red graph and the blue graph intersect. Because if you have the same number divided by the same number, you're going to get 1. So I'm going to label this purple point as where they intersect. And on the green graph, that's going to be 1. If my blue graph is 1, it's going to be exactly the same. In the dividing questions, you're going to have to use some skills from recognizing graphs. And in this situation, can you see that your red graph looks like some sort of, I'll draw in red, some sort of square root graph? And the blue graph looks like some sort of line. In fact, mx plus b, I might even be able to quickly write it out as minus x plus 1. A square root is an exponent of a half, and x is an exponent of 1. If the degree is bigger in your denominator, your graph will have an asymptote at 0. So based on this, when I click to reveal, my green graph went through all the points. Again, it doesn't go less than -2 because the red graph doesn't exist. But for domain, the domain of my new graph is where both graphs exist, but I have to include the non-permissible value and show that x can't equal 1 either. So obviously the dividing ones are the most complicated because they might have non-permissible values. They're also the most complicated because you might have other asymptotes as well. So they require the most skills of remembering things from previous units. Okay, let's go to example 1. And example 1, they add some other complications that we're going to have to learn. We have f of x equals x plus 2, and g of x equals the absolute value of x. Right, so I'm going to color code these. That one in blue, that one in green. And just off to the side, I'm going to say to myself, do I know what these graphs look like? Yes. X plus 2, approximately like that. A straight line, y-intercept of 2, slope of 1. Absolute value of x. This goes back to our very first unit. There's our absolute value of x graph. So we want to have a picture of it because from that picture, can you see that the domain of f of x is everything, and the domain of g of x is everything? And our graphs give us that right away. From the equations, you could figure that out as well. When figuring out domain from equations, you ask yourself, is there any x value that's not allowed? X plus 2, is there like, were you ever taught in middle school, oh, you can add 2 to everything except for, you never can add 2 to 3. No, nothing exists like that. So you can also look at the equation to determine that domain would be everything. And here's some new language. So, new language here. Write an explicit equation for h of x. So, what does that mean as an explicit equation? This is going to mean you're going to write h of x equals, and here, this side has to be in terms of x, not in terms of functions. Because otherwise we would be done. You have h of x equals f of x plus g of x. You're like, I'm done. Okay? This isn't very hard, except when they get to the second part where they say, then determine its domain and range. So for part B, the explicit part, h of x, well, what can I write instead of f of x? I could write x plus 2. And what can I write instead of g of x? I can write the absolute value of x. This is the explicit equation. From that explicit equation, since everything was allowed for x and everything is allowed for the absolute value x, it might be really easy for you to see that the domain of this is everything. The challenge we have in this graph is figuring out the range. So what we could do is we could just start adding the graphs together, but then you'd have to know a lot of points. So for example, on this graph, I have 0, 2. On my green graph, I have 0, 0. So on my combination graph, which I'm going to do in purple, if I add the y values, I would also have 0, 2. And if I kept doing this, right, I have 1, 3. I have 1, 1. If I add my y values, I have 1, 4. If I add my y values for 2, you're going to find that you have 2, 6. If you add your y values for -1, you have -1, 2. If you add your y values for -2, you're going to have -2, 2. And after these points, sort of like interesting, you kept going with your points, you're going to notice this goes straight like this, and this goes straight like this. But your question is going to be, how many points would you have to do to be certain that it does that? And since you haven't done any questions like this, I think you'd have to do a lot of points. And even after you did a lot of points, you might not feel certain yet. Okay? So I'm going to show you how we can get, by the way, so now as a result from the graphs, our range is bigger than or equal to 2. But algebraically, in order to solve this, we have to get introduced to something new. And that new idea is that some graphs are called piecewise functions. Piecewise functions are graphs that you can't necessarily say all the time just with one equation. It would be easier if you said it with 2 equations. Can you see that this graph looks like 2 straight lines glued together? So it would be much easier. In fact, we're going to write this graph as the following. I guess what is it called, g of x? No, it's called h of x. So I will label it as h of x. And our h of x graph has 2 parts. This part is always equal to 2. So whenever x is less than or equal to 0, it's just equal to 2. That's one piece. The second piece, this is a straight line. Y equals mx plus b. It has a slope of 2 and a y-intercept of 2. So there's the 2 pieces to this graph. One piece is always equal to 2. One piece is always equal to 2x plus 2. Now, I got those 2 pieces by looking at the graph. My next step is I'm going to get these pieces without having to do the graph. Because the graph you might have to do 10, 20, 30 points before you feel comfortable. And that seems like a waste of time. The very first piecewise function that I'm going to introduce to you is actually one that you have an explicit equation for. do you see that the absolute value of x is actually just two lines put together? So I could write it as a piecewise function. On the left side, it's a line with a negative slope. So whenever your x values are less than or equal to 0, and check it out. What's the absolute value of negative 2? You know it's positive 2, right? But if I plug it into this formula, does it still give me positive 2? If I plug in negative 2 and put a negative in front of it, yeah, it makes it positive. And when x is bigger than 0, well, the absolute value doesn't matter, right? What's the absolute value of 5? 5. Do you see how the piecewise equation does that as well? Instead of having to memorize that absolute value just makes things positive, if I plug in negative 2.1, the second part of the piecewise function tells you which piece you use. So since x is less than or equal to 0, I use the top piece. If I plug in negative 2.1, I should do negative 2.1, which makes it positive 2.1. Perfect. So now when I have algebraically h of x equal to this, I could now write it as a piecewise function. And I'll do this in 2 steps, but these were the 2 pieces where the absolute value got broken up, right? And so it could be x plus 2, and if x is less than 0, then that's negative x. And when x is bigger than 0, that's just x. Now, if we can do algebra, which we couldn't do before when we had the absolute value, what's x plus negative x? That goes away. You just get 2 when x is less than or equal to 0. And when x is this, these are like terms, I would get 2x plus 2 when x is bigger than 0. A few little things for piecewise notation. Notice how I had in my domain the equal sign with one of them but not the other? You have to decide where you're going to, like you can't have a value in both pieces. Like 0 has to, you have to choose which one. So you put an equal sign with either one of them, but it doesn't matter. But you can't put the equal sign with both. Okay, so that's new, piecewise functions. You deal actually quite a bit with piecewise functions in calculus. And so this gets us introduced to that. And then part C, they have P of x equals f of x times g of x. It asks you to write the explicit equation. So f of x was x plus 2. G of x was the absolute value of x. And I'm not even going to attempt to multiply things by just looking at the graph. I'm going to see if I can find the explicit equation in piecewise. So here's my explicit. As a piecewise function, absolute value gets broken up when x is less than or equal to 0 and when x is bigger than 0. When x is less than or equal to 0, the absolute value of x is minus x. And when x is bigger than or equal to 0, the absolute value is x. I could either keep it this way, or I could multiply this out. This one will be x squared minus 2x, and this one will be x squared plus 2x. When x is less than or equal to 0, when x is bigger than 0. But I'm actually going to now graph these two pieces for you so that you can graph P of x all at once. And in graphing these two pieces, just to show you, I'm going to do that one in blue, this piece in green, and then after I've drawn the pieces separately, I'm going to go over the whole thing in purple to say this is my final graph for P of x. So P of x has two pieces. It has this blue piece, which is that one, and this green piece, which is also that one. And the reason I put boxes around the factored version as well, because I actually find the factored version helps me more with graphing. Because I'm going to use my polynomial skills from chapter 1 for graphing this. You know this is a parabola that opens down. So you know its end behavior. And if I look at its factored form, can you see that it has x-intercepts at 0 and at -2? And it would be a parabola, and I'm just going to draw it in a dotted line here. That would be the whole parabola if it was dotted line. I did it dotted to begin with because are we allowed to draw the whole parabola? No, we can only draw a piece of it. Which piece of the blue parabola are we allowed to draw?
When x is smaller than or equal to 0.
When x is smaller than or equal to 0, so it's this piece that we're allowed to draw. I'm going to draw the green one. It's also parabola. It also has the same x-intercepts, but it opens up. This would be the green parabola. Which part am I allowed to draw? Just the part that is bigger than 0. So my purple graph looks like this. And if I got you to do a table of values, I'm absolutely certain your graph would look terrible. Sorry. I trust some, no, I don't. All of you, I think, first try you would make a terrible looking graph. In fact, if I made a table of values and tried to make a graph, my graph would look terrible. Because you wouldn't get this shape. But once you do it algebraically, you know what parabolas look like. I'm certain nobody would have got a nice sharp point there. You probably would have made your graph look like an x cubed graph in the end. Just because you're used to that more. But this one actually has like a sharp point at this value. Now it didn't ask us to graph it. It just asked us to find the domain and range. And now that we're done, our domain and range are listed there. That's interesting. Okay, circle questions 3, 5, and 10.